Okay, I'm going to finish off the what we did in the last session. So that is, yeah, so here's the repository, and I updated it with the how far we got with the advection diffusion solver, where we started to create this diffusivity law, adding it to this advection diffusion solver. All right, so let me load OpenFOAM and go to where I have the code. Actually, that means make a new terminal, actually. All right, so let me just git pull, make sure I have the latest code. Okay, so just to briefly recap, we have this solver that solves this advection diffusion equation. So DDT term, a advection or convection type term, and then a diffusion or like conduction or something type term. And we were adding a class called diffusivity law, and we were going to use that to calculate diffusivity as a function of temperature. So we had added a H file and we had added a C file. So the H file, so far we are storing a DT, a diffusivity field inside this class, and then a couple of coefficients, which we're going to use to calculate the diffusivity as a function of temperature like this. And we added a function called test, which basically does nothing. So we just checked that that compiled and that worked. So that was the H file given the declaration, but then in the C file we give the actual implementation to definition. So we have a constructor, it constructs this DT vol scalar field. So it has an IO object and a mesh and then a default value. And we're setting these dimension scalars just to be 0 to begin with. And then our test function is writing out hello world. So I'll just check this still compiles. Oh, okay. So let's keep going. So for this test function to do what, or not this test function, for us to be able to calculate this dt, we have to read the properties from some dict or from somewhere. So in the solver, we could pass the values of a0 and a1 and give those as arguments, but I guess it's a bit more convenient, I think, if I just give the name, a string name of a dictionary. And then I'll assume that this class will look up that dictionary itself. And that's probably the most convenient because then I don't, if I want to use this, I don't have to prepare a dictionary in advance. So I'll assume that it gives it a string name. Just close this. Okay, so I'm going to give that string name. So if I try to compile it now, it'll complain because it'll say there's no constructor that takes a dictionary. So it says no constructor matching for this law that takes a mesh and a word. It says the only options are ones that take a mesh, that one there. So let me go to the H file and I'm going to update the declaration of the constructor. So I'll assume it takes a string, but in OpenFOAM there's a convenient class called a word. So if I give a dict name, so a word is a generalization of a string with some extra functionality that is just convenient in OpenFOAM. And it's const because I'm not going to let this class change it. It's just this is the name and you can use that to look up something. And generally good practice in OpenFOAM is anything bigger than a scalar, you should take a reference to it. So a reference just is like passing a pointer basically to the object. So if I copy that, go to the C file, update my constructor here. So now the constructor is updated. If I compile it, it should compile now. I'm just not using that name for anything, but at least I'm just checking that the code still compiles, which it does. So now I have that new constructor. So this is called a member initialization list of a constructor in C++. And then down here in these curly braces is the main body of the constructor. So you'll see I'm initializing these values to 0, but what I'm going to do now in the main body is I'm going to look up this dictionary by this name. So I'm going to make an object called an IO dictionary. So input output dictionary. I'll just call it dict. And then it has a constructor. One of the constructors is you just pass it an IO object. So just to remind you, the IO object is a class that just keeps it's used for reading and writing, so it just keeps track of information like name of whatever file you're going to read or write from disk, where it's located, and whether it has to be read or whether it needs to be written, things like that. So in this case, I will not look it up from a time directory, but I think I can just write constant here and then it'll look it up from the constant folder. But I could write system, it'll look from the system folder, or time name from the time folder. And then rather than, I just copy this from DT above, from this DT field. So this first entry here is the name. So I'm just going to use dict name. So whatever name is passed in, and this is going to must read it from the constant directory. And no write. I don't want to rewrite the dictionary, but you could rewrite it if you wanted. So I'll just check that compiles, make sure I didn't make a mistake in that. Okay, so that it will correctly look up the dictionary, but I'm not actually using it yet. So the final thing to do is I just want to look up the values of A naught. So there's a few different ways to do that. If you have a dictionary, like an IO dictionary or dictionary, there's a few different functions you can that are defined inside a dictionary. So you can do functions like lookup, and you just give the name, say A naught, and it will look up that thing, and it could be a word or a list or anything. OpenFOAM will adapt appropriately. Or you can do lookup or default. And lookup or default, and you normally have to tell it in that case what it's looking for, let's say a scalar. That takes two arguments then. So it's like, well, look up this thing called A naught, but if you can't find it, just give it a default value of 10 or whatever you can hard code in. And there's also, there's functions like dict dot found. So if you wanted to have some conditional, say if you find A naught, then let's say look set A naught equal to something, blah blah blah. Else, if it's not found, then set it's something else. So you can do that. So one thing, where do you find all of these functions? I guess just looking at other OpenFOAM code is maybe the quickest way to learn. But if I open another terminal and load OpenFOAM, if I type src, that's a shortcut for cd, or an alias for cd foam underscore src. So this is where the main OpenFOAM libraries are. So this is where most of the OpenFOAM code is. So there's lots and lots of stuff here. But if you're looking for a particular class, let's say I'm looking for something called IO dictionary, then if I just look for IO dictionary and then maybe star or .h or .c, I can search in this, and it's in the main OpenFOAM library. And you can see ln include are just folders that include links. So the actual main file is included here. So if you want to see what functions a class has, you can open it up and it looks similar to the class we're designing. But you generally want to go down to the bottom. At the very bottom of the class is normally where you'll find the public functions, the ones that you can use. And then another thing to note is this IO dictionary is derived from another class. So in this case, it's derived from something called base IO dictionary. So that means any functions in that base class you can also call. So if I jump down the bottom of this, I don't think this IO dictionary actually has many functions that are useful. But if we went to that base one, so if I look for, was it called base IO? Yeah, okay, it was right beside it. So if I go to that base IO, that will derive from something called a reg IO object and a dictionary. So actually the dictionary is most of the functions. Everything else is more about the input output. So if we go down here, there's not that many functions in this one, but if I search for a class actually just called dictionary, there's lots of them, but dictionary.h should be here. Yeah, this one here. So some of the functions I was talking about, like lookup, if I search down here, you can see there's a function lookup entry, and it'll give a short description of what it does, or there's a function called get or default, or get or add. So you can, even if it's not found in the dictionary, you can add things to it or read if present, blah, blah, blah. So there's lots of extra checks. Okay, so I just want to look up the value. So I will do it like this. And actually, another way to do it is I can just make a dimensioned scalar. And if you have a dictionary and a dimension scalar, there's a there's a constructor where you can just give the name of what you want to look up and then pass it to dict. So that's another way to do it, and then that will automatically look it up. So just get rid of that. Just check that works. If I have that in the right order. Yeah, yeah. So I'll do that for A naught and A1. And maybe I'll just write those out and just say A naught equals A naught, new line, A1 equals A1, and construct that. And maybe I will make another, while that's compiling, I will make another tab. Go back to the tutorial we had, which is here, advection fusion foam, my test case. I think we just ran block mesh. We had set fields, I think, as well. I open up all run. Oh, restore the zero directory first. So I will make a copy of that. Set fields was to set the initial temperature. I have just a shortcut to open this up in my existing power view. So we had something like this at the start. So we had something like that was our initialization. So if I run the solver now, you'll see it will complain. So it'll say entry A naught not found in transport properties. So I'll use lots of tabs here. So we have DT, but I'll add A naught now. So if I just give A naught and I just give a number, then it assumes it's dimensionless. But if I actually want to give it dimensions, which I do in this case, then I'll actually use the OpenFOAM convention for dimensions. So if I'm going to set the diffusivity to be A naught plus A1 times the temperature, then A naught should have the dimensions of diffusivity. So that is meters squared per second, I think. Let's try to run again. And then it is complaining actually. So there's somewhere else it's complaining as well. Must read, must read. Okay. I'm getting an error also about the use of must read or read if modified, which I think is coming from above. Yeah, so it's just saying if the DT here is must read, then it's basically saying, well, you shouldn't give a default value if it's must read because you don't need the default value. So in this case, we're actually going to set that to be no read. Okay, so compile that, and then the dimension problem we're getting. This is viscosity, so it's complaining when I set the value here. Oh, and I have also a mistake here. So this should be A1. Compile that. So this is diffusivity per temperature, and it's trying to set to something that's diffusivity. I think that's just from the second line. Was accidentally trying to set A1, which is diffusivity per temperature. So if I do that, let's say A1 is not found, and I will just copy this over. So A1 is per degree, and then we set that to be something smaller. I don't know if those numbers are okay. We'll see. Okay, so that runs, but it's not actually being used. But you can see that, okay, it does actually read them properly and then print them out. And then that hello world is coming from the test function. Okay, so we have all the data we need in the class. Now we just need to make it useful. So what I'm going to do is inside the temp simple loop, I'm going to assume that there's a update function. So that update function is going to update the diffusivity. And then I'm going to assume that there is a function called dt, which will just return a copy or a reference to the actual dt field. So I'll update it here and then I'll return it here. So I could, in this dt function, actually update it on the fly and then return it. But maybe if I want to access it later, then that means that it will recalculate every time. So it's maybe more convenient to have a function separately that does the updating and one that returns access to it. And my update function needs access to the T field. So it'll have to look something like that. So let's go back and add those functions. So we will have an update the DT field function. It returns nothing, just void, and it takes a vol scalar field reference to the T field. So reference, if I didn't put that in, it would actually make a copy of the full field. So that's normally a very inefficient or bad thing to do, considering that you might be running with a very large mesh. So that would be making a full copy of that entire field. So you normally would pass things by reference. And it's constant, so it means it can't be changed. Now the other function, let me just get rid of that. Oh, the other function we wanted was, sorry, Mac shortcuts are getting in the way. Is just we will, I'll do the second one here. First one, return access or read only access to the DT field. So we want to add a DT function that takes no arguments, and it should return access to the DT field. So once again, it's a reference. We don't want to actually make a copy of the DT field, the DT field, and it's const, so it means that whoever gets that reference cannot change the field. For very small functions, it's often fine to just implement them directly in the H file. The only disadvantage of that is every time you compile, let's say your main solver code, if you're including the H file, it has to recompile this actual function, not just its declaration. But normally, if you're just returning something that's negligible. But if it's a large piece of code, it's more efficient to put in the C file because then it'll only be compiled once essentially. So that's that function DT, and then we have the update function. So we only have to put the update function here, like that. So yeah, okay, let's check if that compiles. So we have update function is not doing anything at the moment. And then we have our DT function, which returns our DT field, but the DT field, we at the moment have constructed it to be equal to 0, I think. Yeah, defaults to 0. Okay, so let's see. We got, okay, so we have an error on line 80. So it's saying it's out of line definition. So if we go to that, line 80. So here, where did I go wrong? Update const diff law, go to the H file, update. This looks okay. Yeah, this looks okay. So what is it complaining about here? I missed a bracket somewhere, I wonder. Let me just move this one up here. Headline definition member, qualifier. Oh, there's the problem. The stray semicolon here. So this semicolon here was ending that declaration. Excellent. So this should compile now. So now the last thing to do is we just have to implement this update function. So it probably makes sense rather than letting DT be 0 at the very start. I should probably just initialize it to be A0, just assuming no in the no dependency on temperature. But in here, I'm just going to say DT is equal to A0. You can implement anything, but just as a simple linear relation, A1 times temperature. So then DT is a field, a vol scalar field. A0 is a dimension scalar. This is a dimension scalar, and this is a vol scalar field. So these vol scalar fields, to remind you, it's a list of one value for every cell center, and then it will store values for every phase center as well, called the patches. So when you do an operator like this, like you multiply a vol scalar field, OpenFOAM has implemented it that it'll apply that multiplication to the internal field and to the boundary patches. So that will make a temporary vol scalar field, and then it'll add a dimension scalar, and it knows to add that to each cell and each boundary face, and then that gets assigned to the DT field. So if I do that, then if I go back to my solver code, so now the solver code, we're creating the diffusivity law, we are updating the diffusivity field, and then we are asking for access to it to be passed back there. So then if I run the solver this time, let me just delete some of the results so I know I'm actually, ooh, I don't want to delete the dot orig or to 9. That's probably a bit safer. Okay, so if I go advection diffusion and run this, we will now have a changing diffusivity field. So I think it actually gets written. All right, so it's, let me refresh. Oh, excellent. Why is this not reading it properly? Okay, so now we have all the results. I can even look at this diffusivity field. So I guess if I look at the very start, it is 0. So that makes me think that we have not updated it. dt. So let me go back to the solver here. So one thing is we actually don't need the dt field in create field. So unless that actually is messing it up, that it's actually writing the wrong field out. So in our create fields in the solver, we were separately, the original way we were doing it was creating a D field here, DT field here. So actually we don't need that anymore, and we don't need this transport properties anymore. So I'll get rid of that. So when OpenFOAM goes to write the results, um, write as well. Let me get rid of these things we don't need. It's the heat flux. I'll get rid of that as well. So when OpenFOAM goes rewrite the fields, the way it does that is for all IO objects, it just keeps a track of a list of all of them, and then whichever one is set to auto write, then in the case when you've set it to write at a certain interval, it will just go through each field and write them out. So you can have an issue then if you have two fields of the exact same type and the exact same name, then whichever was added most recent might be the one that writes or was added originally. So I think that might be part of the problem here. But in any case, I think our diffusivity was probably way too high. So let me try to set this to, say, 6, and maybe get rid of this dependency to begin it. Let's see what happens this time. Okay, so all right, now the diffusivity is 1 and it's not changing. That makes sense. And then our T field is moving across like that. Okay, so that's fine. So then if I change this to be 1 minus 6 times temperature, so maybe like -8 or something, and just to check it works. So this would mean that diffusivity or like conductivity is basically increasing with temperature. And so if I go back here, you can see that, okay, in this case, it's doubled wherever it's hot. So for the properties I've set up here, you probably won't see very much. I can do what I did the last day, slice through it, and do a warp by dt times 2. So then, yeah, you get this kind of like what we had before. But in this case, you're getting higher diffusivity, I guess, where it's higher temperature. So obviously you could implement any dependency, but that's the basic idea. Okay, so that is the basic way to implement your own class. So there's a bunch of things you could do here. I won't do it now, but maybe it's something for another session. But for example, maybe instead of diffusivity law, it might be just a general kind of thermophysical law. So maybe I would add a function called dot source, and then that would return a field, which is just like a heat sink or heat source. And then I would just like I created the DT field or the update field, I would write another or function. I'd write another function that will return a source. And then you can imagine that that source could be time or spatially varying. So for example, if I wanted to apply a heat source at this region here, I could find all the cells in this region and then apply a heat source and then move that around. So, for example, if you're implementing a simple like laser heat source boundary condition, or not boundary condition, source term, you could do it that way. And then in the transport properties, then you would, or whatever you want to call your dictionary, you could read in the start time of the laser, the end time, the power, the speed, and then you would find where the cells are and then apply a heat source moving around. But okay, that is shorter this week, but I think maybe this is a good place to stop. So let me stop the recording. There we go. Stop recording.